This lecture is on chapter 6.1 to 6.2 on balancing chemical equations. So where have we been so far in general chemistry? So in chapter 1, we learned atomic structure. In chapter 2, we were introduced to atomic orbitals and electron configuration. Chapter 3, we worked on ions and ionic bonding. Chapter 4, covalent bonding. In chapter 5, we have 3D configuration of molecules. So now we're going to move on to discuss the actual combination of these molecules together and the reactions called chemical equations. So recall Dalton's atomic theory. So Dalton's theory combined three different previously established laws to come up with four tenets to define all matter. That elements are made up of tiny particles called atoms, that each atom is characterized by the masses of its atoms, and that atoms of the same element have the same mass, but that atoms of different elements have different masses. That chemical combination of elements to make different chemical compounds occur when atoms bond together in small whole number ratios. And that four, chemical reactions only rearrange how atoms are combined in chemical compounds. The atoms themselves do not change. So for discussions of chemical reactions, we're dealing with postulate number 4 of Dalton's atomic theory, that when we undergo chemical reactions, that the identity of the atoms do not change, they only rearrange the ways they are combined. So if we take a look at the reaction, two hydrogen diatomic gas molecules reacting with one diatomic oxygen yields two molecules of H2O, which we know as water. And so if we think about this on the microscopic atomic scale, we can visualize two different molecules mixing with one molecule to form two molecules. So the number of atoms for each element in the reactants is equal to the number of atoms for each element in the products. So none of these individual atoms actually disappear. They only change the way in which they are rearranged. So if we think about this, if we take it now from the microscopic up to the macroscopic. So remember, we introduced the idea of the mole in order to discuss these materials in terms of quantities that we can actually conceptualize and think of and something we can hold. So the same sort of idea that these what are called stoichiometric coefficients, which are these large numbers on the outside of each of these different molecules. So this arrangement here that's shown here is called a chemical equation. And so that gives you the microscopic number of molecules that react. You can have that same sort of idea expand to the number of moles. So um, so this same chemical equation states that 2 moles of hydrogen molecules plus 1 mole, so if there's no number in this stoichiometric coefficient, that means that it's 1. So 1 mole of oxygen gas yields 2 moles of liquid water. And so these coefficients give the ratio of molecules involved in the reaction, also give the ratio of number of moles. Okay, so you can think of this as a microscopic in terms of molecules, macroscopic in terms of number of moles. So now let's convert this macroscopic in terms of moles to what I call usable macroscopic. So when you are in the laboratory, you're not going to say, hey, give me 1 mole of oxygen gas. You're going to put it in terms of a quantifiable, measurable amount. So how do we actually get this number of moles to saying I need 0.56 grams of hydrogen gas reacting with 4.44 grams of oxygen gas to yield 5 grams of liquid water? Okay, so these are actual usable macroscopic amounts that we can measure out and quantify in the laboratory. Okay, and so this brings us back to one of our other fundamental laws of mass conservation. The mass of our reactants is equal to the mass of our products. Okay, so we need to be able to figure out ways to convert between our microscopic to our macroscopic to our usable macroscopic. Okay, and so this will be the focus of today's lecture as well as the upcoming lectures. So the first step is to identify the correct balanced chemical equation. So the balanced chemical equation is the equation showing the fixed proportions of how molecules interact with each other to describe a chemical reaction. And so these equations follow the law of mass conservation, whereas the mass of the reactants is equal to the mass of the products. And so the numbers and kinds of atoms remain the same in both the reactants and the products. So the states of matter of each of the species are shown in parentheses after each molecule, which parenthesis S stands for solid, parenthesis L stands for liquid, parenthesis G stands for gas, and parenthesis AQ stands for aqueous. And aqueous also means dissolved in water. So here we have two H2 diatomic gas or hydrogen molecules, that's gas, plus one O2 diatomic oxygen molecule, which is a gas, yields two water molecules, which is a liquid. So let's see how we're actually going to go through the process of balancing a chemical equation. So we have a set of three individual steps here to make sure that we systematically go through and make sure that we solve these problems correctly. So the first is to write the unbalanced equation using the correct chemical formula for each reactant and product. So here we're going to be discussing going through a reaction between CH4, which is methane, plus O2, which is diatomic oxygen gas, to yield the products of CO2, which is carbon dioxide gas, plus H2O, which is liquid water. So step one is just writing that unbalanced equation. Step two is to make a list of the numbers and kinds of atoms that are the same on both sides of the equation. Find suitable coefficients, which are the numbers placed before the formula, to indicate how many formula units of each substance are required to balance the equation. So we can see on the left-hand side, we have one carbon. On the right-hand side, there's one carbon. On the left-hand side, we have four oxygens. On the right-hand side, we have two oxygens. Excuse this message here. On the left-hand side, we have two oxygens. On the right-hand side, we have 2 plus 1 gives us 3 oxygens. Okay, so now we have to add coefficients in order to change the number of atoms that are present on the reactant and product sides in order to balance this equation. Okay, so if up on the board here we draw or you write out the chemical equation, and then we indicate how many of each specific atom are present on either side. We can see here that we need to increase our hydrogen number by 2. So we can do that. So excuse me, I forgot my states of matter. Okay, so we can increase it's important to know we can't actually decrease the number of any atom that we have. So we want to increase by putting a stoichiometric coefficient of 2 in front of H2O, which means we multiply each of these number of atoms by the stoichiometric coefficient of 2. So 2 times 2 means that there's now 4 hydrogen atoms. And now there's 2 times 1 oxygen means 2 oxygen atoms for water, 2 oxygen for carbon dioxide, means our new number for oxygen is now 4. So now to balance our number of oxygens, we need to put a 2 stoichiometric coefficient in front of O2, which means we now have 4 oxygen atoms. So our step 3 now is to take a look at our numbers here, make sure that they are all balanced. And now, if necessary, we need to reduce the coefficients to their smallest whole number values if necessary, by dividing all of the stoichiometric coefficients by their common divisor. So if we were to incorrectly have identified our stoichiometric coefficients as 2, 4, 2, and 4, we could see that each of those coefficients are divisible by 2. So if we divided them by 2, we would get our simplest form. So your turn. So I invite you to pause your video here and take a shot at balancing this equation. Okay, so for this equation here, we again are going to write out our unbalanced form. So we have HgNO3 2 aqueous plus Ki aqueous yields HgI2 solid plus KNO3 aqueous. Okay, so we're going to go through and identify how many of each species are on both sides. So Hg, which is mercury, we have 1 on each side. Our nitrogen, we multiply this 2 on the outside to all of our numbers on the inside. So nitrogen, we have 2. Oxygen, we have 2 times 3 is 6. Potassium, you have 1. And iodine, we have 1. On the product side, we have 1 mercury, we have 2 iodine, we have 1 potassium, we have 1 nitrogen, and we have 3 oxygen. Okay? So now we need to recognize that we need to increase our number of nitrogen from 1 to 2. So if we add a 2 stoichiometric coefficient to the outside of the KNO3, that's now going to increase. 2 times 1 gives us 2K. 2 times 1 for the nitrogen gives us 2 nitrogens. 2 times 3 for the oxygen gives us 6 oxygen. So now we're good on nitrogen, we're good on oxygen. Now we're off on K and I. And so we recognize in the reactants here, we have our Ki. If we increase the stoichiometric coefficient to 2, we can see that 2 times 1, we have 2K. 2 times 1 gives us 2I. And we can check out that we have all of our individual atoms balanced. And we can go through and seeing a stoichiometric coefficient of 1, 2, 1, 2. It is in its lowest possible form. And so that is reduced and correct. All right, next is to balance this complex equation. So take a few moments here to work through this on your own. Okay, if we write it up on the board, we have KClO3 solid plus C12H22O11 solid, which yields KCl solid plus CO2 gas plus H2O liquid. Okay, sorry, I kind of ran out of space on the board there. Okay, so let's go through and identify how much of each that we have. So if we take a look at K, potassium, we have 1. For chlorine, Cl, we have 1. For oxygen, we have 3 plus 11 is 14. For carbon, we have 12. For hydrogen, we have 22. On the right-hand side, we identify we have 1 potassium, K. We have 1 chlorine. We have 1 carbon. We have 2 plus 1 gives us 3 oxygens. And we have 2 hydrogens. Okay, so let's start off by first balancing our number of carbons. So we can see here that we have 12 carbons on the reactants and only 1 carbon on our products. So if we add a 12 here as our coefficient, we can see 12 times 1 will give us 12 carbons. And for our oxygens, 12 times 2 gives us 24 plus 1 gives us 25 oxygens. Okay, and so now if we take a look, now our carbons are balanced. Now let's take a look at our number of hydrogens. We have 22 hydrogens on the left-hand side, and we only have 2 hydrogens on the right-hand side. So if we multiply by a stoichiometric coefficient of 11, so 11 times 2 will give us now 22 hydrogens. And now we have 11 oxygens plus our previous number here, which is 24. So 24 plus 11 is going to be 35 oxygens. Okay, so now we have 35 oxygens on the right-hand side, and we have 14 on the left-hand side, which means that we need to have 21 more oxygens added to our left-hand side. Okay, and so we can see we can do that by adding 8 of our KClO3. So if we do that now, we have 8 potassium, we have 8 chlorine, so 8 times 3 gives us 24, plus 11 gives us 35 oxygens. Okay, now we see our K and Cl both need to be increased from 1 up to 8, and luckily we have a KCl. We can increase that number to 8, which gives us 8 total. So now we can go through and take a look, and we see all of our numbers of atoms are equal on both sides. And we can see that we do not have a common divisor, which means that this is the most simplified form, and thus our final answer of 8, 1, 8, 12, and 11 as our stoichiometric coefficients. All right, that's it for the day. Thank you.